All right, folks, here in section 7.5, we are going to look at inverse trigonometric functions. Going to be quite a bit in this section. So let's start off by reviewing the inverse trigonometric functions. The graph of sine x, it's over here to the right, and clearly the graph of sine is not a one-to-one function. You can see there's a horizontal line that intersects the graph in 5 points. It would intersect the graph if you continued on in all directions in an infinite number of points. There are an infinite number of ways we could restrict the domain and still preserve the range. Remember, the range is -1 to 1. There are an infinite number of ways that we could restrict the domain. But in trig, you would have seen we're going to restrict the domain to go from -π/2 to π/2. And that preserves the range. And on that restricted domain, the function is 1 to 1, and it has an inverse function. So I'm going to look at the graph of sine x. This is the graph of sine x in the bottom right here, just on the interval -π/2 to π/2. And clearly it's 1 to 1, and yes, we preserved the range to go -1 to 1. Now the inverse function of the restricted sine function, it's called the inverse sine function. Folks, there are two common ways to denote the inverse sine function. Either y equals inverse sine x or y equals arc sine x. They both represent the same function. Your text uses f of x equals inverse sine x. So I'm going to try my best to always use the inverse sine notation rather than arc sine. And here was the definition you would have seen of the inverse sine function back in trigonometry. The inverse sine function, denoted y equals inverse sine x, is defined by y equals inverse sine x if and only if sine y equals x, where -1 is less than or equal to x is less than or equal to 1, and -π/2 is less than or equal to y is less than or equal to π/2. Or in other words, the domain of inverse sine is -1 to 1, and the range is -π/2 to π/2. Now, since y equals inverse sine means sine y equals x, I always kind of thought when I saw y equals inverse sine x, I always thought, y is the angle or real number whose sine is equal to x. Furthermore, we can think of the inverse sine function as its job is finding an angle in the interval -π/2 to π/2. Well, the interval -π/2 to π/2 is the right half of the unit circle. So it's the part of the unit circle that is highlighted in blue in this figure. Which brings us back to the fact that a thorough understanding of the unit circle, it's imperative for success in fully understanding not just trigonometry, but inverse trig functions. All right, now similarly, f of x equals cosine x is not 1 to 1. I mean, here's a graph of cosine. It's clearly not 1 to 1. There are an infinite number of ways we could restrict the domain, but in trigonometry, you would have seen that we're going to restrict the domain to the interval 0 to pi, and it preserves the range from -1 to 1, and that would produce something that is 1 to 1, and then we can officially talk about the inverse cosine function. So there's the graph of cosine on the restricted domain from 0 to pi, and we can visually see that the range -1 to 1 is preserved. And you should have seen a definition along the following back in trigonometry for inverse cosine. So the inverse cosine function, denoted y equals inverse cosine x, is defined by, y equals inverse cosine x if and only if cosine of y equals x, where -1 is less than or equal to x is less than or equal to 1, and 0 is less than or equal to y is less than or equal to pi. In other words, the domain of inverse cosine is -1 to 1, and the range is 0 to pi. Quick note, since y equals inverse cosine x means cosine y equals x, we can think of, I've thought of this as being, y is the angle or real number whose cosine equals x. Since y equals inverse cosine x means cosine y equals x, I've always thought that the job of y equals inverse cosine x, y is the angle or real number whose cosine equals x, but its job is, to find an angle in the interval 0 to pi, or the top half of the unit circle. So there's the top half of the unit circle highlighted in blue. So inverse cosine is finding an angle that matches up with the top half of the unit circle. Inverse sine is finding an angle matches up with the right half of the unit circle. Continuing a review of inverse trig, similarly to what we have seen with inverse sine, inverse cosine, we're going to have to restrict the domain of f of x equals tangent x so that we have a one-to-one portion and it preserves the range of tangent. Remember, the range of tangent x is negative infinity to infinity. There's the graph of tangent x. Clearly it's not 1 to 1. In the figure that you see here to the right, what I've highlighted in the solid blue, that's the graph, that's the portion, that's the restricted domain. So we look at tangent just on the interval -pi/2 to pi/2. Clearly that's 1 to 1, and it preserves the range. So we can talk about an inverse tangent. Now, I haven't put up here on the slides or reviewed the graph of inverse sine, nor have I put up the graph of inverse cosine. The graph of inverse tangent is really important. It is really, really important. So here is the graph of inverse tangent. This is something that you really, really need to remember. This graph. This is the graph of inverse tangent. Notice the graph of inverse tangent has a horizontal asymptote at -pi/2 and a horizontal asymptote at pi/2. It's this graph that, knowing this graph, allows me to remember two limits that will keep popping up in calculus. Specifically, the limit as x heads to infinity of inverse tangent is pi/2, and the limit as x heads to negative infinity of inverse tangent is -pi/2. So that is a graph that you need to know. Hopefully you heard that back in trigonometry. Now, since y equals inverse tangent x means tangent y equals x, I've always thought, that y equals inverse tangent x, that was representing or telling me that, y is the angle or real number whose tangent equals x. Or furthermore, I always thought the job of inverse tangent, its job was finding an angle in the open interval -pi/2 to pi/2, which matches up with the right half of the unit circle, excluding the endpoints. So the job of inverse tangent, it finds an angle on the right half of the unit circle, but excluding the endpoints. That's why you see open circles at 0, 1 and 0, -1. All right, let's do a quick example reviewing how to find exact values of inverse trig functions. And I'm going to have 5 of them here. So please, write down all 5 parts because I'm going to head off to the chalkboard and I'm going to do these. All right, folks, here we are. We're going to review a little bit more here of the inverse trig functions. Determine the exact value of inverse sine of 1/2. So here's what I need you to think. Here's what I need you to remember. Inverse sine is finding an angle off the right half of the unit circle. Then when you do the sine of that angle, you get 1/2. that angle would be pi over 6. Part B, inverse sine square root 3 over 2. So think, you're finding an angle on the right half of the unit circle. Now let me just kind of sketch the right half of the unit circle. You're finding an angle on the right half of the unit circle, that when you do the sine of that angle, you get square root 3 over 2. Well, I think that would be the angle that's about right here, which is pi over 3. Inverse sine negative 1/2. Think, you're getting an angle off the right half of the unit circle. Then when you do the sine of that angle, you get negative 1/2. Well, here's the point on the unit circle that would have a y-coordinate of negative 1/2. So there's the angle. A common mistake people make is to say that this is 11 pi over 6. And that's not correct. 11 pi over 6 is not in the interval negative pi over 2 to pi over 2. But I know why people say 11 pi over 6. Because that's this angle measure. That's not right. We are giving this angle measure so that we are in the interval negative pi over 2 to pi over 2. So that means inverse sine of negative 1/2 is negative pi over 6. Part D, inverse cosine square root 3 over 2. Okay, I'm thinking, inverse cosine. I'm trying to find an angle on the top half of the unit circle. Then when I do the cosine of that angle, I get square root 3 over 2. So let me quickly sketch the top half of the unit circle. Remember, that's an x-coordinate. So the angle, when I do the cosine of that angle, I get square root 3 over 2. That angle is pi over 6. So inverse cosine square root 3 over 2 is pi over 6. Part E, inverse cosine negative square root 3 over 2. So I'm thinking, I've got to find an angle on the top half of the unit circle. Then when I do the cosine of that angle, I get negative square root 3 over 2. And that angle would be 5 pi over 6. Let's head back to the slides and see what the next topic is. All right, hopefully that came back to you. Doing the inverse sine, inverse cosine, inverse tangent. I will mention on page 481, you'll see definitions of the other 3 inverse trig functions. And that's all I'm going to say about them. All right, this next example, we're given y equals inverse sine x. Y is in quadrant 1. We're going to determine cosine y. This is a really, really important example. In fact, we're going to use the result of this example in the following example. So get this written down because I'm going to head off to the chalkboard to work through it. All right, folks, in this example, we're given y equals inverse sine x. Y is in the interval 0 to pi over 2. Determine cosine y. So saying y is in the interval 0 to pi over 2 is basically saying y is an angle that's out there, terminates in quadrant 1. So, folks, y equals inverse sine of x. You have to remember that means the sine of y is equal to x. Okay, now I could use some identities, like Pythagorean identities, to try to determine the cosine of y. But you know what, I thought, let's review a little right triangular trig. So right triangle trig, we have sine of y is equal to x. We know angle y is somewhere out in quadrant 1. So let me just sketch a quick right triangle. Here's angle y. Remember, sine equals opposite over hypotenuse. Sine of y equal, well, you can think of x as being x over 1. So opposite over hypotenuse. Then we can find the length of the missing side here in the right triangle by using the Pythagorean theorem. And if we do that, we're going to get the missing side is the square root of 1 minus x squared. And from the right triangle, we get that cosine of y equals, remember cosine in a right triangle, cosine is adjacent over hypotenuse. So adjacent over hypotenuse, we get cosine y is the square root of 1 minus x squared. And I want to make a note here. This statement, it happens to also be true if y is in the interval negative pi over 2 to 0. Okay, this is going to be something really important we just did because we're going to head back to the slides and we're going to start talking about the calculus of the inverse trig functions. In fact, I know in the next example I do, this is going to be important. We're going to need to remember it. Let's head back to the slides. Hey, previous example, we determined that if we were given y equals inverse sine x, we have cosine y equals the square root of 1 minus x squared. We're going to use that result here in a minute. I also stated at the board that that result was true in the interval negative pi over 2 to 0. And one more time, this information is going to be used in our next example. Our next example is going to revisit an old topic, implicit differentiation. So here it is. Y equals inverse sine x. Y is in the closed interval, negative pi over 2 to pi over 2. Let's determine dy dx. We are going to determine the derivative of inverse sine. And we are not going to use the definition of the derivative. So we're going to do this. We need implicit differentiation to do it. We need the result from the prior example. And it's going to, the result of this example is we're going to have a new derivative rule. So get this all written down. I'm heading off to the chalkboard to work through it. All right, folks. Y equals inverse sine x. Y is in the interval of negative pi over 2 to pi over 2. We're going to determine dy dx. We are going to come up with the derivative for inverse sine. Basically, we're coming up with a new rule here. And I am not going to use the definition of the derivative. You may notice in the upper right-hand corner of the board, I wrote down something that I just mentioned on the slides, the result of the last example we did. And I told you to write it down because it was going to be important in doing this example. So, remember, y equals inverse sine x means the sine of y is equal to x. Okay, I mentioned before we came to the board, I mentioned on the slides that we're gonna employ an old technique, something we already know, implicit differentiation. So that means I'm going to d dx both sides of this equation. All right, we know the derivative of sine. We know that's cosine. And remember implicit differentiation, we're assuming y is a function of x. So the chain rule says we have to differentiate that function of x. So when we differentiate that function of x, we get dy dx. And over here, the derivative of x is 1. So I'm going to pull it up here. I'm going to divide both sides of the equation by cosine y to have dy dx equals 1 over cosine y. And from the last example, we know what cosine y is. We know what cosine y is. So we're going to substitute the square root of 1 minus x squared in here for cosine y. And get 1 over the square root of 1 minus x squared. So we just came up with the fact that if y is inverse sine x, the derivative of inverse sine x is 1 over the square root of 1 minus x squared. we came up with a new derivative rule. So let's head back to the slides and let's put this into a theorem. All right, that prior example illustrated we have determined a new derivative rule. So let's make it a theorem. And we're just going to go right to the chain rule part. So use a differentiable function of x. The derivative of inverse sine u, it is 1 over the square root 1 minus u squared times du dx, which would be the derivative of u, obviously. The derivative with respect to x of inverse cosine, well, it's just the negative of 1 over square root 1 minus u squared du dx. Number 3, the derivative with respect to x of inverse tangent u. It's 1 over 1 plus u squared du dx. So we have some new derivative rules here, folks. We should probably practice them. So in this example, we're going to differentiate the following. And let's see. We have four parts. So got some new stuff here, got some old stuff. In any event, write down all 4 parts in this example because I'm going to head off to the chalkboard and work through them. All right, this example, we're practicing our new derivative rules. New derivative rules for inverse sine x, inverse cosine x, and inverse tangent x. So the first one we have here is f of x equals inverse sine of x squared. So the derivative is 1 over the square root of 1 minus, okay, now remember it said u squared? Well, that's like the u. So I'd have x squared squared. That's x to the 4th. Times, now the chain rule, du dx, the derivative of the x squared, which is 2x. Or if you prefer, you could write that as 2x over the square root of 1 minus x to the 4th. Part B, f of x equals inverse tangent of square root x. Alright, so our derivative is 1 over 1 plus u squared, so think that's like the u. So the square root of x squared, that's x, times du dx. Now we have to differentiate this. Well, remember square root of x is x to the 1/2. The derivative of x to the 1/2 is 1/2 x to the negative 1/2. Or I could write that as 1 over 2 square root x. I'm going to leave it like that. Oh, there was a C and a D. F of x equals x inverse tangent x. Well, folks, here, yeah, we get to use the product rule. You have the function x times the function inverse tangent x. So the product rule says the derivative of the first function, which is 1, times the second function, plus the first function, times, then the derivative of inverse tangent x is 1 over 1 plus x squared. Or if you prefer, I guess you could write this as, you could write it like that if you'd like. And then part D, ooh, D's a good one. You have the function tangent of inverse sine x. Alright, so we have to remember, well, what's the derivative of tangent? That's right, derivative of tangent is secant squared. So this is secant squared inverse sine x times, now you have to remember the chain rule, you have to do the derivative of inverse sine x, which is 1 over the square root 1 minus x squared. All right, there's a couple derivatives I'd like you to practice here. So in the section 7.5 exercises, I want you to pause the video, go to the section 7.5 exercises, do number 52 and 60. After you've done them, restart the video. I'll be here working through them. All right, number 52, we're supposed to differentiate f of x equals inverse sine of natural log x. So I get the derivative to be, okay, the derivative of inverse sine is 1 over the square root of 1 minus the u squared. So that's like the u, so I'd have the natural log of x squared times du dx. So the derivative of ln x is 1 over x. That's it. Your book may have in the back, I'm just going to rewrite it another way. ln x, that quantity squared, some people write that like that. Natural log squared x. You don't have to do that. I'm happy with this. I'm happy with that. Number 60, f of t equals inverse cosine t, that quantity squared. So we get the derivative. Well, we start off, 2 comes out front, subtract 1 from the exponent, leaves me with a 1, times, now we have to remember the chain rule, I have to do the derivative of inverse cosine t. Well, that's negative 1 over the square root of 1 minus t squared. And if you want, I guess you could write this as a negative 2 inverse cosine t all over the square root of 1 minus t squared. But let's head back to the slides and see what's next. Seems like once we learn about derivatives, the next thing we do is integration, but let's head back to the slides and see if that's the case. All right, so there we are. We practiced our new derivative rule. Hopefully you were able to get the 2 exercises I asked you to do. Now that we know how to do derivatives, well, we might as well immediately look at integrals that are going to give us inverse trig functions. So in this theorem, use a differentiable function of x. A is greater than 0. So the first one says that if you integrate a 1 over the square root of a squared minus u squared du, that antiderivative gives you inverse sine u over a plus c. The integral of 1 over a squared plus u squared du equals 1 over a inverse tangent u over a plus c. Then you can look at the third one here, and I always make a deal, with my students that, if on a test you needed to know number 3, I would supply you with that part of the theorem. I would tell you that the integral of 1 over u square root u squared minus a squared du equals 1 over a inverse sec and absolute value u over a plus c. It's rarely used, but I just included it for completeness. So now, folks, we're getting to that part of integration where recognition is going to start to become kind of important. You have an integral. Remember when we first started antiderivatives, I said it's like a game. Well, it is not only just like a game, but they're like little puzzles. So we're starting to hit that part of integration where, you have to maybe put a little bit of more thought into it initially. What does it look like? Does it look like it's a U-sub? Does it look like it's going to be an inverse tangent? That kind of stuff. So let's do a quick example. This example will probably just use the new stuff that we've learned. So there are 2 parts. Write down both parts. And as I'm heading off to the chalkboard, here's what I kind of see in part A and part B. Part A, I see something, the denominator, I see that square root 16 minus x squared under the radical sign. I'm thinking, boy, that kind of looks like inverse sine to me. Part B, that kind of looks like inverse tangent to me. But let's head off to the chalkboard and let's work through both parts here. All right, folks, when I look at part A here, integrate 5 over the square root of 16 minus x squared dx, I say to myself, that kind of reminds me of inverse sine. It looks like an inverse sine where I could say A is 4, because 4 squared is 16. U is x. Du is dx. So just knowing how inverse sine, knowing the integral, the structure of the integral, the way it looks, that produces inverse sine, knowing that formula, I immediately have the antiderivative is 5 inverse sine u over a, x over 4, plus c. Done in one step. Part B, I say that kind of reminds me of inverse tangent. But be aware, well, now it even looks more like inverse tangent. It's going to produce an antiderivative that involves inverse tangent. Because remember, with the inverse tangent, the structure of it is the integral of 1 over a squared plus u squared. So you can't look at this and say that is the a and that's the u. That's not true. U is that differentiable function of x. So I'm saying it looks like it's going to produce inverse tangent. Let me write down what a is. 1. A is 1. 1 squared is 1. U is 3x, because 3x, that quantity, squared, that's what gives me a 9x squared. Which means du is a 3dx, or a 1/3 du is dx. Now, folks, that's kind of important. That's kind of important to know, because this 1/3 is going to be part of the antiderivative. Because when I use the formula for integrating 1 over the a squared plus u squared, I got this 1/3 out front. And then remember that the formula to integrate 1 over a squared plus u squared, it's 1 over a, inverse tangent, u over a, then plus c. And then I would not leave my answer like that, because we know 1 over 1 is 1, so 1/3 times 1 gives us a 1/3 inverse tangent. 3x over 1 is 3x plus c. 1/3 comes from the fact that u is 3x, so 1/3 du is dx. It's something to be aware of. Alright, so we're going to head back to the slides. We got a really big example coming up. We're going to do a lot of integrals. So let's head back to the slides so you can get them all written down. Alright, that wasn't too bad. The final example is a long one, because I'm going to crank through 8 different integrals. In this final example, it involves integration where everything seen so far is fair game. I'm trying to lay the foundation of, they're like little puzzles. And you got to think, how are you going to attack the puzzle? What does it look like you're going to do? In this example, I'm also going to highlight some tricks that will be handy, especially as you head into Calculus 2. These are tricks that, no one should expect you to know these tricks right now. You have to see the trick to then say, okay, now I know I can use this trick. So if I show you a trick and you say, I would have never thought of to do that, that's why you're watching the video. That's why you're in calculus. You are learning that trick. So a lot of parts here. Write down all the parts. So there are the first three. There are the second three. And there are the last two. So like I said, we're going to do 8, and there's a total of 8 here at the board, to try to give you an understanding of once you have a lot of integration techniques under your belt, anything is fair game, and you can do these. And so we're going to go do them at the board. All right, folks, here's the first one of the 8 that we're going to look at. And I'm going to be writing a little bit more on the board and doing a little bit more, babbling than normal. So, bear with me. Hopefully it's for your benefit. So when I see this integral, I really see this as the integral from 0 to 1 over the square root of 2 squared minus x squared. And now we know the integral of 1 over the square root of a squared minus u squared. We know that for this integral, it produces an antiderivative of inverse sine u over a plus c. So when I see the integral, when I see the original integral like this, I immediately have, well, a is 2, u is x, which implies du equals dx, which is good for me because I know I'm not going to have a little extra multiplier in the antiderivative here. And I can immediately get the antiderivative because I know it's inverse sine u over a. So it's inverse sine u over a, x over 2. And I need to evaluate that from 0 to 1. So I get inverse sine of 1/2 minus inverse sine of 0. Inverse sine of 1/2, I'm thinking of an angle on the right half of the unit circle. That when I do the sine of that angle, I get 1/2. That angle is pi over 6. And inverse sine of 0 is 0. So this definite integral had a value of pi over 6. So, now bear with me because I have to erase the board to get part B up here. So part B was the integral 1 over 4 plus x minus 1 quantity squared dx. Well, that kind of looks to me like the general form that produces inverse tangent. I mean, we know the integral of 1 over a squared plus u squared. That has an antiderivative of 1 over a, inverse tangent u over a plus c. So it looks to me like this has that form where a is 2, u is x minus 1, and that implies du is dx, which is good for me. There's no extra multiplier in there. So I can immediately write down the antiderivative. The antiderivative is 1 over a, so that's 1/2. Inverse tangent u over a, well, that's x minus 1 over 2 plus c. That's all there is to part B. So let me get part C written down up here. Part C was to integrate t over t to the 4th plus 16 dt. Which I'm going to say, you know what? that denominator could be written like that. In fact, the denominator could be written like that. Doesn't it now look an awful lot like the structure of inverse tangent? Let's write down the parts. I mean, A would be 4. U, okay, U is t squared, which implies du is a 2t dt, 1/2 du equals t dt. Now I did that because I was spying this t dt here. You know, 1/2 du would go in for the t dt. In fact, if I were to make all these substitutions, I've just turned this integral, I've turned it into 1/2 the integral 1 over a squared plus u squared du. You know, I'm saying a is 4, u is t squared, 1/2 du is the t dt, 1/2 out front. I mean, I can't make it look any more like inverse tangent than that. So we get the antiderivative. We get the antiderivative to be a 1/2 times 1 over a, that's 1/4, inverse tangent u over a, t squared over 4, plus c, or if you prefer, a 1/8 inverse tangent t squared over 4 plus c. And that's all there is to part C. All right, let's see what part D was. Part D. Ooh, that's a good one. Part D was a definite integral. Let me write that down. The integral from 0 to square root 2 over 2 inverse cosine x over the square root of 1 minus x squared dx. You know what? D is such a good one that I'd like you to pause the video and I would like you to try this one. And then once you're done, restart the video. I'll be here at the board working through it. All right, this one requires us to start off with a U-substitution. And the U-substitution doesn't fit the guidelines that I gave you back in section 5.5. Remember I said the guidelines were just guidelines. It's not going to handle 100% of every situation. And I'm saying that because here, I'm going to let U equal inverse cosine x. Then we know du is negative 1 over the square root of 1 minus x squared dx, or negative du is 1 over the square root 1 minus x squared dx. So when I substitute in, so here I go, substitute in, so that's u. The 1 over square root 1 minus x squared dx is negative du. So this whole mess just becomes a u du with a negative sign out front. And now we have to make a decision. Do we go route 1, leave off limits of integration, you know, get an antiderivative, resubstitute, and then bring back these original limits of integration that belong to the variable x? Or do we turn these x limits, do we turn them into u limits? And you know what? Let's turn them into u limits. Okay, remember this says x is 0. So I put 0 in here for x. Inverse cosine of 0. That's right, pi over 2, because the cosine of pi over 2 is 0. This is x equals square root 2 over 2, so put square root 2 over 2 in here for x. Inverse cosine of square root 2 over 2. That's right, pi over 4. So now I can get my antiderivative. Use these u limits. And what do I have? Negative 1/2 pi over 4 squared minus negative 1/2 pi over 2 quantity squared. So let's see, pi over 4 squared is pi squared over 16 times negative 1/2. That's negative pi squared over 32. That's plus pi over 2 squared. That's pi squared over 4. 1/2 times pi squared over 4 gives me pi squared over 8. So that is the value of the definite integral. Now I could go a little bit further. It wouldn't take too much to get a common denominator. So let's clean it up just a little bit more. We could get a common denominator of 32 pretty quickly. We already have, negative pi squared over 32. Pi squared over 8, that's 4 pi squared over 32. You know what, doesn't that look nicer as an answer than that? I think it does. Okay, hopefully you got part D. Now let's look at part E. So when I look at part E, what do we have here? The integral from negative 3 to negative 1 over x squared plus 6x plus 13 dx. Okay, I'll be honest, way back when, I would be tempted. I would have done a U-Substitution. And I would have let u equal the denominator. It's not going to work, but let me write it down. Then du is a 2x plus 6 dx. And no matter how much massaging I do here, I can't get something for just the 1 dx. I can't. So it failed. The U-Substitution failed. So here comes your first trick. I told you there would be some tricks. So here's your first trick. Complete the square in the denominator. Again, old algebra technique of completing the square. So I'm going to just kind of talk through the completing the square. I remember the process of completing the square. The process was you take half of this, which gives you 3, then you square that, which gives you 9. And what that tells me is that x squared plus 6x plus 9 is a perfect square. So why don't I look at the denominator that says x squared plus 6x plus 13 and just rewrite it as x squared plus 6x plus 9 plus 4. I mean, 13 is 9 plus 4. And then I could put these 3 terms in a group and I have a perfect square. It's x plus 3 quantity squared plus 4 dx. And now this looks an awful lot like, what part was it? Part B. It looks an awful lot like part B. I mean, it looks like it's the structure of an inverse tangent. Except here, keep in mind, a is 2. I mean, a is the number. U is x plus 3, which means du is dx, which is great because I'm not going to have any extra multiplier to worry about. So I can immediately get my antiderivative. It's an inverse tangent. Remember, it's a 1 over a. 1 over 2. Inverse tangent, u over a. That's x plus 3 over 2. And I evaluate that from -3 to -1. So I would have 1/2 inverse tangent. Okay, -1 plus 3. That's 2. 2 over 2 is 1. Minus inverse tangent. Okay, -3 comes in for, oh, that's just 0. Well, that's pretty friendly. All right, so inverse tangent of 1/2, or I'm sorry, inverse tangent of 1. So what angle on the right half of the unit circle, when I do the tangent of that angle, I get 1. That's right, pi over 4. And inverse tangent of 0 is 0, so we end up with the value of this definite integral as being pi over 8. All right, so now I showed you a trick, and this is setting up the next example, the next part of this example, part F. So, fortunately you have this in your notes. You have all this in your notes. Let's look at part F. It looks so much like part E. Part F is integrating a 2x over x squared plus 6x plus 13 dx. I mean, that looks an awful lot like part E we just did. The only difference is in part E, well, it was a definite integral, but in part E the numerator was a 1. I mean, here the numerator is a 2x. So, this is going to have another trick here. I mean, I know a U-substitution is not going to work. I know if I let u equal x squared plus 6x plus 13, I know du is 2x plus 6 dx. I mean, it's close. The numerator, it's a 2x. If only it were a 2x plus 6. If it were a 2x plus 6, it would work. The U-substitution would work. So here's a trick. Let's put a plus 6 in the numerator so this U-substitution will work. Let's rewrite this. Denominator is still x squared plus 6x plus 13. Let's get a plus 6 up there. But I would also have to subtract 6. I mean, I can't just say plus 6 because it's not the same numerator. But if I say 2x plus 6 minus 6, I mean, that numerator simplifies to 2x. And notice what that would allow me to do now. It would allow me to take this and split it into 2x plus 6 over x squared plus 6x plus 13 minus 6 over x squared plus 6x plus 13. That's the meaning of a common denominator. And if I pull the beastie up here and I write it as two integrals now, we know how to do the first integral. This first integral is handled by this U-substitution. That second integral, well, we just kind of looked at how to do the second integral. That second integral, we would complete the square on the denominator. I mean, we know how to rewrite that denominator. We saw this in part E. It's x plus 3, quantity squared, plus 4 dx. And we know here a is 2, u is x plus 3, which means du is dx, nothing to worry about. Here, u is x squared. We're doing a u sub here. U is x squared plus 6x plus 13. Du is a 2x plus 6 dx. So we substitute in here. We have the integral of 1 over u du. And here we know that has the structure of kicking out inverse tangent. So remember, it's going to kick out, well, we have a 6 times 1 over a, inverse tangent, u over a. Here we know what the antiderivative of 1 over u is. It's natural log absolute value of u. And then we resubstitute for our u. And we finally have finished the problem. So the last two examples, you've seen a couple of tricks. The first one was just completing the square in the denominator. This trick is a little bit more sophisticated. So if you're sitting there and you're saying, I would have never thought to add 6 and subtract 6 from the numerator to do this problem. That's okay. I never thought of doing that before I saw the trick that I can add and subtract the same thing into a numerator. And that became a trick. It became part of my arsenal on how to attack integrals. So that was part F. Two more parts. Part G. Oh boy, let's erase this. So bear with me as I erase. I like that example. That's a good one. Had a lot of good stuff embedded in it. So part G was integrating x minus 1 over square root of x squared minus 2x dx. You know what? Why don't you try part G? So pause the video, you do part G, and when you're done, restart the video. I'll be here at the board cranking through it. Alright, let's see how you did on part G. After a lot of analysis, I look at it and I say, wow, you know what? This is just a basic U-substitution. If I let u equal what's under the radical, du is a 2x minus 2 dx. So I have square root u in the denominator. And then this x minus 1 dx, well, if I factor out a 2 and then multiply by 1/2, the x minus 1 dx is 1/2 du. So I substitute 1/2 du in for the x minus 1 dx. I rip the 1/2 out front. I rewrite 1 over square root u as u to the negative 1/2. And then I use the power rule. So 1/2, leave a little space. Add 1 to the exponent. So negative 1/2 plus 1 is 1/2. And here I put the reciprocal of the new exponent. Reciprocal of the new exponent is 2. And finish it off. That's 1. Resubstitute gives us x squared minus 2x to the 1/2 power plus c. So folks, hopefully you got that. Just a good old-fashioned U-substitution. One more part, part H. And this is also another one of my favorites. Yeah, getting into these integrals, they're just kind of like little puzzles that need to be solved. So part H was integrating an e to the x over e to the 2x plus 9 dx. Okay, we could try a lot of false starts here, a lot of false steps, but I'm just going to cut to the chase. You know, when I see this, it's this denominator. I see this denominator, it's like, okay, 9. I know 9 is 3 squared. E to the 2x is e to the x, quantity squared. Boy, it's kind of looking to me like it's going to kick out an inverse tangent. I mean, a is 3, u is e to the x, which means du is e to the x dx. I mean, this integral is nothing more than a u squared in the denominator plus an a squared in the denominator. The e to the x dx is du. This is inverse tangent. This is inverse tangent, where we end up getting pretty quickly 1 over a. Remember inverse tangent, the formula for this integral kicks out a 1 over a. 1 over a, that's 1/3. Inverse tangent, u over a. So e to the x over 3 plus c. And that's it. I probably did more integrals here in this example than what you'll have in the actual homework. And most of them in the homework are going to be straightforward, kicking out inverse sine or kicking out inverse tangent. I showed you a lot here. I showed you some tricks. I showed you how things were disguised. You know, so a lot of this stuff, you know, may not necessarily be pertinent now, but it will be when you get into Calculus 2. So that's it for this section, Section 7.5. So now you can do the Section 7.5 exercises, and thanks for watching.